As we have seen in the previous video, when we apply a magnetic field, domain walls will start moving because they will feel a pressure that is due to the minimization of Zeeman energy requirements. But while a domain wall is moving throughout the specimen, it will encounter some second phase material regions where the magnetic properties are different from the rest of the material. These are called magnetic inclusions, and we will see that when a domain wall intersects such an inclusion, it may get pinned. So isolated regions of second phase materials with magnetic properties different from the host material are called magnetic inclusions. So what can be a magnetic inclusion? These could be some crystal imperfections, or it could be some impurity materials. So the inclusions can be pores, voids, cracks, insoluble impurity materials, impurities, etc. And what happens when the domain wall intersects these inclusions? When the domain wall intersects such an inclusion, its energy will be lowered that is due to redistribution of magnetic poles. And why is the energy lowered? Because this is leading to reduction of magnetostatic energy. And I'm going to make a simple calculation here to demonstrate this idea. So here I have a spherical void inside a sample, and initially this is magnetized in the upward direction, so on the plus y direction, and you can see the distribution of poles. The south poles will be at the bottom and the north poles will be at the top. So this is my magnetic void. So I'm applying a magnetic field H in this direction, a magnetizing field. Let's say it's in this direction, and the magnetization will be pointing in this direction. So that means I have a collection of north poles here and a collection of south poles here. That will cause the material to magnetize, so this is outside the material, this will recall the south poles on this side and north poles on that side, so that the magnetic material will be magnetized like this. So I have a collection of south poles and north poles like that. And there is the spherical void in the middle, and when I apply when I have a domain wall that is going to travel inside this material, I see that if this domain wall hits this void, it's going to basically cause the south pole and north pole redistribution here. So the magnetization will be pointing down on the left side and up on the right side. So this is a 180-degree domain wall. And now you can see that I have sort of a closure forming in the middle because I have the redistribution of domains. So initially I have the magnetostatic energy. The magnetostatic energy is EM magnetostatic minus 1 over 2 mu 0 saturation magnetization dot product with the demagnetizing field multiplied by the volume 4/3 pi r cube if I have a radius r for this sphere. And the demagnetizing field is NdMs, so it is minus 1 over 3 ms. This is demagnetizing factor for a sphere. So complete this symmetric situation. Then I will find that the magnetostatic energy initially is 1 over 2 mu 0 4/3 pi r cube ms times ms over 3, which is 2 over 9 mu 0 pi r cube ms squared. Now this is initial situation. Now I want to consider the 180-degree domain wall. So with 180-degree domain wall, you can see that I have formed a closure structure here. The magnetostatic energy on each side will be minus 1 over 2 mu 0 ms dot ht multiplied with 2/3 pi r cube. So this will be 1 over 9 mu 0 pi r cube ms squared on each side. And these energies don't add up, so it's actually the magnetostatic energy of this configuration. So indeed, I find that the magnetostatic energy is lowered by the domain wall. So by the presence of the domain wall, I have lowered the magnetostatic energy. So I just noticed that I have placed these incorrectly here. So if the magnetization is pointing upward like this, then I would need to have south poles on this side so that the magnetization would be pointing up on this side as well, and north poles on this side, so the magnetization will be pointing up like this. So it's the same everywhere. And here I have the magnetization pointing down, so sorry for misplacing these poles. Now I will have the south poles on this side, uh, the north poles on this side, and south poles on this side, and north poles on this side, so that the magnetization would be pointing like that. And with that, the arrow direction will change, so it will just be pointing to the left here and pointing to the right here. Okay, so we have corrected the magnetic pole configuration. All right, so if we have isolated regions of second phase material that is different from the host material, we have magnetic inclusions, and these inclusions can be crystal imperfections, pores, voids, cracks, insoluble materials, etc. When a magnetic domain wall intersects such an inclusion, its energy is lowered due to the reduction in the magnetostatic energy, which comes from redistribution of magnetic poles. In the initial configuration here, I have the whole magnetic material magnetized up. So there's a magnetic field that's pointing up. So that means I have south poles on the upper side and north poles at the bottom side of the pore, so that I have the magnetization vector pointing up everywhere. So there is no domain wall here. And now I introduce a domain wall. Magnetization is pointing down on the left-hand side. So I have north poles on the top, south poles at the bottom. And to the right, I have magnetization pointing up, south poles at the top, north poles at the bottom. That means I will be creating a closure structure pointing from south to north on the top hemisphere and on the bottom hemisphere. So because I have a reduction in the volume of the saturated magnetization by 1/2, the magnetostatic energy of this configuration is lowered by 1/2. But there is this additional domain wall energy here that is being introduced into the system, so that we should think about also. So this domain wall motion can be interrupted by the presence of these cracks, because when the domain wall enters this magnetic inclusion, the magnetostatic energy of the configuration is lowered, so this may be an energetically favorable configuration. So the domain wall can get pinned. So this means domain walls can be pinned by the magnetic inclusions. Now I want to remind you what we said about observations of domains. So let's go back to our discussion of domain observation here. If you look at the magnetization curve, here we see these steps in the magnetization curve. That's called Barkhausen noise. It's basically a proof of the motion of the magnetization by domain wall motion, because these steps are due to the pinning of domain walls at the magnetic inclusions.